All right, y'all, it's Barry. I'm here to give y'all some notes for circular motion and gravitation. We're going to hop right into it in a sec, but just want to make sure that we realize the unit that we're on and the big ideas that we're going to be covering. So real quick, a reminder for College Board and AP Classroom curriculum in particular, they put out 5 big ideas. They've been covered a lot in previous units to this point, so just want to point out that all 5 of the big ideas are going to be present in this unit at some point. So let's keep an eye out for those because we will look for them at the end again to see where they were present. All right. First thing we need to do is talk about how things move in a circular pattern as opposed to a linear pattern. So up to this point, we've investigated how things move in a straight line or potentially with vectors in 2 dimensions at once, but it's time to see what happens when they rotate, when they start moving continuously in a circle. So if an object goes from moving in a straight line to rotating about an axis, it is still moving, so we need to still consider it part of motion and part of kinematics that we learn in this class. We can take a straight line and bend it to form an arc. And you see this S value over here, that's what we're going to consider an arc length S. Now this could be more than one full circle if it makes one full revolution, and that's really important to realize. But in the case right here, it's much shorter than that, obviously. It's at some radius r out from the center of that circle, and there's some angle theta that separates those 2 red lines that are on either sides of the arc. Okay? So we'd be looking at that arc length there being the radius of the circle that's given right there to us, times theta, that change in angle that's happened between the 2 red lines, and that theta change is going to be in degrees, it's going to be in radians. So a quick reminder, one full revolution around a circle is equivalent to 360 degrees, and then also equivalent to 2 pi radians. Okay, so let's keep that in mind as we're doing our conversions and we're solving all these different problems. So again, moving from linear motion here, where in the past we've covered some distance, now we're going to cover some angle in our rotational motion. Where before we had some velocity that was the meters per second, the distance covered in some amount of time in a straight line. Now we're going to have an angular velocity that's really going to be a measure of how quickly these objects are spinning in a circular pattern. And we see that rotation happening down here. They do still have a tangential velocity, so if it were to stop spinning and be released from whatever's holding it and spinning it in a circle, it would travel outwards in a straight line, and you see that marked there with the green arrow vector and v. But for the most part, if it continues to spin, we're going to consider it to have an angular velocity versus a tangential velocity. And we see some of the comparisons here, but we're going to build on that coming up, so I'm going to save that. We'll look at those different formulas and how we can apply our linear knowledge to a rotational knowledge in just a second. And then speaking of which, so position in the past, we marked it as X. Now we mark it as theta. So the yellow dot there in the bottom right image, we would mark that, we would be able to tell where the location of that is based on theta, the angle that's shown there, and r, the radius out from that center point that the object is located at. All right, so instead of just saying X equals blank, in the case above, X equals 3, we're saying the location of the yellow dot in the bottom case is theta degrees from that east line, from that positive x-axis, up to where the yellow dot is based on the radius and that theta angle. So if we had it move, we could say for a linear motion here that the object at the beginning there, it has a displacement of negative 4x, right, along that line. So it goes from positive 3 to negative 1. Well, the angular displacement would be represented by a change in the angle. The radius won't change as it displaces, as it moves around here, but the angle will. So here we see it's moved some amount there, delta theta, from that yellow to the black location, just like the one above moved from the yellow to the black location. But it was moved delta x, now we are delta theta. And hopefully we're seeing right away that we're going to do a lot of the same things, but instead of using x for our displacement or location, we're actually going to use theta for our change in angle. All right, and we see that right here. Now we could still measure how far something has moved along a circular path in meters, just like we've measured everything else in meters up to this point. And you see that with S there, that's our arc length, okay? And as we move through the rest of these, we're going to see the radius is truly that connection between our linear motion and our angular motion. So right here we see radius there, R, that change in angle delta theta, and the arc length S. Well, in this case, S, that arc length, is going to be how far it's rotated times in radians, so essentially in unitless numbers times the radius that'll be in meters, and that'll give us an arc length in meters. Now, if this object is rotating, we need to keep in mind that that's the case here, and we would have an instantaneous velocity at all these different spots that we could measure by figuring out that change in arc length divided by change in time as time goes on. So we could say it's traveling as something rotates still at 2 meters a second if it was rotating that quickly. But we would describe the angular velocity by saying it's moved a certain number of radians per second that would be equivalent to that based on how quickly it's rotating around. Now, something really important to note here is the radius, different radii for the same delta theta will result in a different tangential velocity. That is to say, if a record is spinning, if you are close to the center of that record, you are actually moving at a lower velocity in meters per second than you would be if you were on the outer edge of that record, despite the fact that you're rotating at the same number of revolutions per minute. So hopefully that's sinking in there, and we'll do a lot of practice with that coming up. Now, again, radius is going to be our conversion between these two values. So the tangential velocity of one of these rotating objects will equal the radius times the angular velocity. And we're going to have similar connections here with our acceleration. Tangential acceleration, so if it was speeding up, would be that change in tangential velocity divided by the time there. But we're going to be looking more likely here at alpha, our alpha value, that's going to be our angular acceleration. If something's spinning, I'm spinning it more quickly. In the case of like you're spinning tires on your car as you're driving down the road, you hit that gas pedal, they spin more quickly. This will lead to your car having a higher tangential velocity, which is really where that friction meets the road between where the rubber meets the road between your tires and the road there, and your car will accelerate in the same way. And that would happen because of your angular acceleration as you speed up the spinning of those tires by stepping on the gas pedal. Okay. This describes changes in the rate of angular rotation, and we still have that correlation there between the radius and correlating our angular quantity to our tangential quantity. The great thing about these things being correlated and all having similar ratios to what we've done in our linear motion is that we can still apply our kinematic equations. So the first kinematic equation, the second kinematic equation, we're going to still use those same ratios. We're just going to change out our quantities. So instead of having angular velocity, instead of having velocity and acceleration, we're going to have angular velocity and angular acceleration. And we see that the ratios other than that still hold true. Same thing for our second kinematic equation. Our regular velocity is still changing to angular velocity. Our regular acceleration still changing to angular acceleration. And again, because we are now using angle, they change in angle there, that theta value. For our position, we're taking out our position quantities and putting in our theta, our angle quantities instead. Okay, so everything else holds true. Now, time is still going to be a constant here. It's going to be measured in the same way, whether we look linearly or angularly. That was a mouthful, apologies. But that's going to work the same way either way. The time is not going to change. We're going to keep time in these equations to be the same thing. And the third kinematic equation, that's going to hold true as well. So now we're looking at how things move in a circular manner and how we can describe that movement. It's time to start to understand why that happens, okay? So we have something known as a centripetal acceleration. That's where we're going to start. This describes a change in velocity without a change in its magnitude. So a reminder, thinking all the way back to our kinematics unit, we defined speed and velocity as being different things. Speed having a magnitude only, as in like a speed limit sign, regardless of the direction that something's traveling in. But velocity having a direction associated with it. So a velocity has a magnitude and a direction. So what, as we see right here, right? So what we can have is a constant speed, but a varying velocity if we are changing direction while continuing on at the same speed. So if an object moves with a constant tangential velocity but changes direction, it still accelerates. Okay, and I'm even going to go ahead and change this right here. This should say speed, right? If it moves with a constant tangential speed but changes direction, it still accelerates. There's still a change in the velocity there. This generates then a force towards the center of rotation, and we're going to talk about what that actually is here in just a minute, because that's really important. But that's referred to as the centripetal force. It's going to happen because of the centripetal acceleration. We're going to hold Newton's second law true still. So the force is mass times acceleration. Our centripetal acceleration, because there's no change in the actual value, has to be calculated some way other than delta V. So we're going to calculate it here by saying it's the square of the tangential velocity divided by the radius of the circle that it's moving around. Okay, so we see here our centripetal force, instead of being ma, is going to be mv squared over r, or mrw squared. This is plugging in right here that correlation that we made earlier between tangential velocity and angular velocity. So let's expand a little bit on how we calculate centripetal acceleration and what it really means to have this centripetal force in place. So for the previous slide, right, it's based on the tangential velocity and the radius of the curve. So just a quick reminder there first. Now that tangential velocity is something that might be difficult to measure if we don't have the arc length. So what you could find here is we're going to use the quantities that define a circle, 2 pi r here being the total distance that it's covered in one full rotation. So if we have a race car going around a circular track and it's going again and again and again and again, we can find the tangential velocity of that race car as it's traveling in a circular path by determining first the circumference of the track, 2 pi r, and then the period, that time it takes to make one full rotation. All right, now T here is important. It is the period. It's the first time we're really introducing this. It's the period for one full revolution, which is to say it's the amount of time in seconds it takes to make one full loop of the circle in question. So then we've got the total circumference of the circle, the total time associated with the circle here, and that's what's going to help us find that velocity that we could then put into the centripetal acceleration equation and find the centripetal acceleration. Let's talk about what this force actually is. And hopefully this picture does a good job grasping really what's at the heart of a centripetal force here. But I want you to consider this picture to the right. Do you feel that already? Do you already feel that little bit of slide side to side that happens when you are moving around a curve in a car? Now let's say you do this at a constant speed. So you're not slowing down, you're not speeding up, you're taking that curve at a safe 35 miles an hour, let's say. Maybe not this one. This one might be more like 25. But you know what I'm saying here, right? We're taking it at a safe speed, obviously. There is what I'm going to refer to now as an imaginary force that acts upon you as you round the curve, that keeps you in the vehicle you're traveling in. Now, what's really happening is you want to continue on in the path that you're going on as you come into this curve over here. So as you're coming into this curve, your body wants to travel this way right here, tangential to the path, because Newton's first law tells us that objects in motion tend to stay in motion unless they're acted upon by some outside force. Well, until you're acted upon by some outside force, you want to continue outwards this way. Now, the car grips to the road. You've got friction between it and the road, but that's not happening to you. So you'll maybe slide just a little bit in your seat. But there's some restoring force. Your seatbelt catches you. Something happens that pulls you in towards the center of that circle. And that restoring force, that thing that keeps you moving in a circular pattern, is going to be considered the centripetal force. Now, there's a lot of different examples of centripetal forces, and we'll look at those in a second. But again, in reality here, your inertia, your mass, wants to continue to travel in a straight line, in a tangential line to the curve that you're going around. But the car keeps you from doing that. And that's why you feel that little bit of motion there, right? That little bit of slide to the outside, but you continue to stay in that line instead of traveling outwards. So to look at it right here, the centripetal force for a car, because it wants to continue to go straight, but there's that centripetal force that keeps it moving in that circular pattern because of Newton's first law. So in reality, it's a felt application of resistance to change in your inertia. So the centripetal force, to say it one more time, is a felt application. It's an experienced application of resistance to change your inertia. It can be calculated based on the velocity of the object and the radius to the center point. And we've seen this a couple times now, so just to reiterate there. Now, some examples of this, okay? Any restoring force that keeps an object traveling in a circular path can be considered a centripetal force. So there's going to be a little bit of overlap here that I understand can be a little bit confusing. But let's look at this first one, this example we've been using so far. A car has a tangential velocity, and it travels around this path, right? Now notice 3 of these that are continuing to travel around the path here show frictional force pulling them to the inside. It's because of the frictional force between the tires and the road that this car continues to travel around the circle. If that frictional force goes away, let's say it's icy outside, then this car could slide outwards. Notice this one out here does not have the arrow for the frictional force, and it's going to continue on tangential to the curved path. It's going to slide right out and slide right off the highway there. Right? This is why you need to drive slower when the roads are wet, when they're icy, when those types of conditions are present, because that frictional force will be less, and particularly around curves, you're more likely to slide out. Okay? So that's a really important thing to note. Now, if I scoot over here, I can look at the example of a ball being swung around in a circular path with a string holding onto it there. In this case, it's the tension of the string that is the centripetal force, because that is what is keeping the ball moving in this pattern. If the string were to be cut, then the ball would move straight outwards at a tangential velocity and would just continue onwards, right, for as far as it could go. So in this case, it is the string that's actually providing us with a centripetal force that keeps it moving circularly. Now, in the case here of the moon orbiting the Earth, there is a pull of gravity, gravitation, that we'll get to in just a second. That is what's keeping the moon from going straight out. The moon is actually moving in this direction. It has this tangential speed as well. But it's because of this interaction here of gravity between the Earth and the moon that it continues on the path that it's on. So in this case, gravity or gravitation would be the force that is the centripetal force that's keeping it in the path. So any restoring force, any force that keeps an object moving in a circular direction is considered a centripetal force. And that's what that force actually is going to vary based on the example. Now, to get to our gravitation here, let's take a look at what gravitation actually is and how this is actually going to work, right? So this is a force manifested by acceleration towards each other of two free material particles or bodies. It is gravity. We're going to talk about how it's a little different than the gravity that we've talked about previously, but gravitation really defines masses being attracted to each other. We understand that in the dynamics unit because we've talked about gravity and the weight of objects. Now we're going to talk about objects that instead of being drastically different in size are very similar in size. So Newton's law of universal gravitation tells us a particle attracts every other particle in the universe with a force that is directly proportional to the product of their masses and indirectly proportional to the square of the distance between their centers. That's a big long sentence that says this equation right down here. So we have two masses, let's say Earth, Moon. There is a gravitational force that pulls between them, just as we saw in the previous slide. That equal and opposite force, which is why we see them being equal here, equal and opposite force can be calculated by the two masses being multiplied together, directly proportional, right? Divided by the square, right? The square of the distance between them, that radius between the centers of mass of the two objects. Now, the centers of mass can be important in this, right? Because the radius of the Earth is a significant radius. So remember, it needs to be center of mass to center of mass. This G value here is the constant that makes this work out. Check out the very top front page of your equation sheets. You'll find this gravitation constant. Okay, this keeps the proportion of the two masses in the radii appropriate to each other and gives us values that can actually be the true gravitational force between these objects. You see the same thing happening over here, large mass, smaller mass, those forces being equal to each other. Some distance r that they are separated and some mass of each of them. We're going to calculate this the same way, and it is important to note that it's still equal and opposite. The Earth pulls on the moon, but the moon also pulls on the Earth. Now, to look a little closer at the difference between gravitation and gravity, and we see our gravitation constant down here that I mentioned. So we'll talk about that in just a sec. But gravity, objects of drastically different sizes. Okay, the reason we can use such a simple number to define acceleration due to gravity, 9.8, we'll just say 9.8, and knowing that that varies just a little bit, right? Is because we have gone through a calculation for gravitation here that includes the mass of the Earth, this G constant, and the radius of the Earth. And all that's been simplified because on the Earth, those are constant values, or at least small enough in variation from the highest point on the surface of the Earth to the lowest point that they are constant essentially for what we need to use them for. Okay? But when we look at objects of drastically different size, of similar sizes overall here, we can't do that. We can't just say, oh, well, the mass of the one object is going to be constant all the way throughout. That the proportion of the two being more equal and more similar in size causes a very different calculation to be necessary. So for gravity here, while one object's pull on the other greatly overpowers the small object, right? The Earth's pull on you greatly overpowers your pull on the Earth. For gravitation, with these objects being of similar sizes, that's not the case, okay? There is a significant pull on the Earth from the moon because they are of comparable sizes, where there is not significant pull of the Earth by me because my mass is so drastically different than the mass of the Earth, okay? So this leads to very different constants in our calculations. The gravity constant we've looked at, right? Again, it's dependent on a size of great mass. Okay, the very large Earth, that Earth mass is constant. It's plugged in there already. The radius of the Earth plugged in there already. It's all done for you to start with here. The gravitational constant will always be the same because the masses are included in the calculation. When we actually look at the equation that's present there, those masses are both included, and so we include that in it and thus can use this same constant no matter what. Okay? So we would do a quick unit analysis in class, and we'll do that when we get there, but I'm not going to pause the notes for that right now, just to make sure that the units, the crazy units here on this gravitation constant work out. So to jump into objects in orbit, I want to make sure we define what an orbit is. It's the gravitationally curved trajectory of an object. So this is an object orbiting around something else that is curved and traveling in a circular pattern, which is what we're looking at really for this unit as a whole. Objects in orbit are said to be always falling toward the planet, but because these objects are moving sideways fast enough, they never actually hit the planet. And I think that's a great way to envision what's happening here, okay? The moon is always falling towards Earth, but it's moving to the side fast enough that it never actually hits it as it continues to go around here. Same thing for the Earth as it goes around the sun. Okay? So again, these objects are always falling toward a planet, satellites, objects in orbit, but they never actually hit it because they're moving sideways fast enough that keeps them in the orbit that they're in. Kepler's laws help describe a lot of this. All right, we're going to do a lot of activities with Kepler's laws, but to give a quick introduction, the first one is the law of ellipses. As objects orbit, and the reason that we look at gravitation in this unit a little bit separately from our perfect circular motion is because they orbit in ellipses. They don't orbit in perfect circular patterns. So it's going to be a tiny bit different as we apply this to objects in orbit. We still have this centripetal force, keeping everything in line per gravitation in this case, but it's not going to orbit in a perfect circle around an object, okay? The perihelion is the shorter side of the ellipse as it orbits around something. The aphelion is the longer side here, and we would have an object orbiting away. This is why we have stuff like seasons, and the tilt is a little bit involved in that as well, but that explains a lot about how we experience things differently for the most part here on Earth, depending on where we are in our orbit around the sun. Okay, we see that happening down there as well. So that's our law of ellipses. That's Kepler's first law. Kepler's second law is the law of equal areas, all right, commonly known as Kepler's second law. So this describes the speed at which objects orbit. They constantly change speed. The closer they are to the center of mass that they're orbiting around, like the perihelion here, the sun, this spot right here, they're going to move faster than they are way out here, okay? So the orbital patterns, they can be broken into triangles of equal areas, and these triangles each cover an equal amount of time. So to go from A to B here, even though it's less distance, will take the same amount of time as going from C to D. And that's because being closer to this object, as we looked at in the gravitation equation, means that there's a stronger pull, and thus you'll end up with a stronger velocity here, okay? So objects move fast as they are close to the sun, and then as they kind of get, we'll say, slingshot out, when they get spread out a little bit further away, they're going to move slower out here. Eventually, that gravitational pull will still keep them in their orbit, and they will begin to move faster as they get closer again, and then slower as they go away, so forth and so on. And there is a proportion that defines this. That's this law of equal areas. And the last one here is the law of harmonies. So this is Kepler's third law. And this really states that there is a proportion between the amount of time it takes to orbit and the radius of orbit that is constant, essentially. Okay, so the law of harmonies here basically says all objects orbit in harmony. The comparison of the orbital period, which is the amount of time it takes for one full revolution, once going all the way around, and the orbital radius of planets. And so you see some of that data right here for Earth and for Mars. The orbital period, this is how long it takes to orbit all the way around for both us and Mars. It gives you the average distance there. And so we see this quantity that is the time squared divided by the radius cubed. That will be roughly constant for all orbiting bodies. And we see it right there being 2.97 something, right, times 10 to the, I want to say it's negative 19. I want to make sure we blow that up and we look at that appropriately. Yes, to the negative 19. Apologies for having to do that, but I just wanted to make sure to clarify. And when looked at in slightly different values, instead of doing meters and seconds, if we look at it in what's known as astronomical units and the period, and that we can define a little bit more in person in class if necessary once we start talking a little bit more in depth about this. But then the ratio becomes essentially 1. All right. Now, whether they be 2.97 something times 10 to the negative 19 or essentially 1, that just varies based on the units. The fact that they are roughly the same within a small variation is really what's important here. And that's Kepler's third law, Kepler's law of harmonies. So hopefully you saw our 5 big ideas as we went through this. I hope this helped you out to understand what's going on for the unit, and I'll see you in class.